Good afternoon and welcome everybody to Technical Session 4. My name is Dave Phelan and it is my pleasure to be your host for this session. Just go through a couple of the housekeeping rules. So please be mindful of the code of conduct that is published on the APNIC 52 website and also in the chat box. If you want to ask any questions or comment, you can either use the raise hand function in Zoom or you can use the Q&A button in Zoom. For any issues that you have with the Zoom chat, with the Zoom session, you can post those into the chat. Please share a photo of yourself attending APNIC 52 on Twitter or Facebook with the hashtag APNIC 52, as there will be some prizes to give away for the best selfies during the conference. Join the conference chat also between sessions so you can mingle with your peers and talk to the other APNIC staff, speakers and sponsors. All my speakers here, I believe I can see my first one. Our first speaker for this session will be George Michelson from APNIC, and he'll be talking about the demystification of AS0 with regards to RPKI. You all ready to go there, George?
Yes, can I share screen?
Yes, you can.
Are my slides coming through okay, Dave?
Yes, we have your slides.
Thank you. Hello, everyone. I'm George Michelson. I'm the product manager for information products at APNIC, and today I'd like to talk to you about the AS0 system that we operate. So first, let's revisit how number resource management works. This diagram shows the number resource management delegation of authority. You're probably all really familiar with this. We operate in a hierarchical manner under a policy governance process. The NRO is a unifying body, but it doesn't really enter into the mechanistic parts of how we operate number resource management. This talk, however, is about RPKI, number resource management, and it's a little different. In RPKI, the RIRs assert a top-level structure, which we can call the TAL, or Trust Anchor Locator, and this is the top-level reference for all the things that become part of RPKI assertions. Bootstrapping, that's how clients start up and come into the RPKI world, takes place inside the software that we call validators. And they use the TAL files, the Trust Anchor Locator files, to fetch the TA, or Trust Anchor, for each RIR. And everything which follows in RPKI comes from this initial configuration step. But what we're going to talk about today is how APNIC operates its TAL, and in particular, how we actually operate two TALs. The main TAL, which is for most RPKI, and an additional TAL, the AS0 TAL. So today we're talking about APNIC's AS0 TAL and everything that stems from it. Here's what we're going to cover if time permits. It's quite a big list. There are 9 topics on this list, so I'm going to be going quite quickly. If slides are available to you to read, I suggest that you keep a copy of the pack and have a look afterwards, and I'm happy to talk to anyone after this talk or at any time about AS0. So let's dive straight in. What is AS0? What does AS0 mean? AS0 has a special role in routing. It's the AS number 0, and it was set informally long before an RFC was published as late as 2015 as the AS that means don't route me. Documentation actually had to catch up with reality. So it's the signal for do not route me, and it has been for some time until it was formally defined. When RPKI was being defined, the AS0 rower's role was formalized in RFC 6483. This was in 2012. So actually, it took 3 more years after we'd said how to use AS0 in a rower in RPKI to clarify its meaning in BGP. Sometimes documents are like this and have to catch up with the reality of operations. So AS0 rower was codified before AS0 had been formally defined for its property. So let's talk a little bit about these key concepts. 4 key terms: RPKI, TAL, ROA, and Slurm. First of all, RPKI is an acronym for the resource PKI. And PKI means Public Key Infrastructure. Public key infrastructure is about using public-private cryptography, public-private key pairs. And these are used to make certificates, and certificates form a hierarchy of issuer and subject. And the subject becomes an issuer for another certificate with a subject, and so on. These depend on a specific private key, which is the trust anchor key, that has a specific public trust anchor key. They can be anywhere in the chain of the things you see, but typically it's at the very top, the apex, and it's typically a self-signed certificate. The point here is that there is a public and private key pair, and that you are told this public key as a trust anchor. The working informal definition of a trust anchor is whatever it signs is accepted as long as it meets the validation requirements. It's explicitly true, whatever true means, if there are a valid set of signatures over all the certificates in a chain from issuer to subject, and they stop at a trust anchor. There are some quirks. CRLs and expiries can alter this, but this is the fundamental behavior. The important thing in RPKI is the R part, R for resource. We're forming lists of internet number resources using a mechanism defined in RFC 3779, and we encode these structures into the certificates. So this PKI is not about names, it's about numbers in RFC 3779 form, lists of numbers, lists of prefixes, lists of AS numbers. Now, it's very important to understand this PKI is not like the PKI that you would use to sign email or encrypt mail or to do TLS to a website. It's not for those purposes. The RFC makes it very, very clear it is not to be used for identity or privacy functions. Unlike most PKI systems, which issue you with a certificate to do lots of things like prove identity or encrypt a secret message, these certificates are marked not to be used to make any signing over anything like that. It's called being a CA. The primary function that we're talking about here is the CA function, and most PKI systems only give certificates that are of the end entity or EE form. They can sign things, secret messages, prove identities. They can't sign other certificates. But in RPKI, we give out certificates that can be used as CAs to make other certificates. We do this all the time. We actually encourage you to make more CAs and to operate them and to use these CA certificates that we give you to make things that are provable in RPKI. We do also have EE certificates, and we use them to sign objects like the ROA. So the whole purpose of a PKI, of all PKI systems, is to validate things, not to take them on trust, but to check the signatures you see are provable in a chain of signing back to a trust anchor, and to check all the policy conformance. So in our case, the current policy guidelines are about prefixes and AS numbers forming proper contained sets. If you're used to seeing the concepts of more or less specific things in a PKI certificate in RPKI at present, it must be a more specific of its parent or identical, and it can't refer to resources which are not in the parent, and it can't be bigger than its parent. Well, the 3 other concepts, they're really simple. A TAL is just a way of referring to a trust anchor. It helps with configuration. Other PKI don't have TAL files. Some, like DNSSEC, use a signaling mechanism inside DNS to do what a TAL does, but we don't have that. So we rely on the TAL file to say, here is the signature of a public key, and you need to check this against a TA, and here's a pointer to that TA. And we ask all coders of systems which do checking in RPKI, they're called the relying party software developers or validator developers, to either include the TAL in their configuration or to help you install the TAL into the configuration that you want to run. A ROA stands for a route origin attestation or authorization. Both are acceptable. It's basically connecting origin AS to a list of prefixes. It's like the RPSL root object, but with an extra value called max length. It's a little contentious. We won't talk about that today because it has no meaning in AS0. Slurm is a simplified mechanism that is, strictly speaking, not part of PKI. It's a filter file that you can add for validation after cryptographic checks and before you pass data to your BGP system. It provides for statements that are simply taken as true, irrespective of the state of PKI. So, at this point, we should probably note that Slurm is a really important tool. It's part of your local BGP configuration if you choose to use it. But crucially for us in the RIR space, it's not a provable assertion. Nothing inside a Slurm file is subject to PKI validation checks. We were guided in what we were doing to use RPKI to get strong proofs about what we do as a registry. And we decided in a policy and governance process not to use Slurm to do this. Now, the use of Slurm is in continuing discussion in IETF, but even in that process, nobody has defined a signing model over what a Slurm file actually says. So if Slurm became provable in PKI, we could revisit this decision, but for now, we choose to operate a system using cryptography to prove things and not unverifiable information. So moving along, we have AS0 defined from BGP as don't root me. And what does the AS0 ROA mean? Well, the formal definition has a lot of text. It's spread over 3 slides that I'm showing you. Please read this. The key point is that up front, a ROA is meant to be a positive attestation, a cryptographically provable statement in the positive. So to make something that's a positive statement into a negative, do not root me, the prefix requires that the AS that is asserted as origin AS be the AS which you can't use in routing. And then you can positively assert you want this origin AS to be marked as valid. You can prove you said it. That's the provable positive statement. The outcome is the negative part. Because AS0 is defined as the prefix is not to be originated, the provable outcome is you just said the prefix is not meant to be rooted. If there is no overriding logic, we can prove that you said don't use this prefix. So the second part is describing that overriding logic. An AS0 ROA by itself stops a prefix being valid under route origin validation. But an AS0 ROA is not an absolute statement. If there is any other ROA that refers to the prefix, that other ROA takes higher priority. So the decision logic calculating ROV won't mark an origin AS as invalid if it can see a ROA for this AS and origin prefix other than AS0 because it trumps the AS0. So AS0 only prevents things as long as there is no better ROA specifying the root. In effect, it means AS0 can be used as a giant turn it on switch. Either a ROA exists or the prefix is not to be rooted. Lastly, there are some fine tuning. You don't have to, but you should set max length to the value of /32, the full length in v4, or /128, the full length in IPv6, so that it's clear an AS0 ROA applies to all the more specific prefixes right the way down to an individual host address. Now, the RFC does say, don't use AS0 as a giant turn it on switch, but that is not said using what in IETF is called normative language. It's not a binding recommendation. So I personally think this part of the RFC isn't actually being helpful. So AS0 is a cryptographic way to exclude things from RPKI unless you sign other ways. And this excludes things from BGP routing. How do you make one? Well, let's look at how we can do this in myAPNIC. Now, if you operate any other system like hosted CRIL RPKI as a delegated CRIL as a delegation under our service, or in an NIR or in another RIR, you're going to have to consult their manual. But the principles would be the same, even if the GUI was totally different. The key point is you have to specify AS0 as the origin AS of the prefix you want to make a rower for. So let's talk about how to do this in myAPNIC. I've used some screenshots as a logged in user. Here's the default landing page when you log into myAPNIC. And you can see a link to the resource manager pages. If you click on this, pages still need a little work. That's coming later this year or next year. But for now, there's lots of tools and we need the ones that are about resources. It's a little indistinct, but it's in the toolbar underneath that green box. So we click on that resources word, and that takes us to a page which lists all the things you can do with your delegated resources. And two of them are useful today. RPKI is just a little bit off screen. We'll come to in a moment. Sorry, have to scroll. So we select RPKI, and that is how you turn the service on. You have to have the right authorization in myAPNIC to do this, but this is an on-off switch for how you can enable RPKI. I've already got things turned on. Here's a list of resources I can sign over, and it includes 1.1.1.0/24. The range is Cloudflare are using in an experiment in association with APNIC Labs. Okay, let's go back up. So if you scroll down, you see a section called Route Management, and this is where you actually make a rower. So we select that option. And this brings us to a page that shows the routes that have already been declared, but it includes the Create Route option. So we click on Create Route, and a pop-up comes up, and this lets us specify a prefix to make a rower for, and we're going to mark the origin AS to be AS0. It's that simple. You just specify AS0 in myAPNIC as the origin AS. And maxlen, which exposed here, is not necessary. You can actually ignore it. Okay, so let's look at some examples of people making their own rowers. So we should be clear here that this is AS0 rowers made by delegates, by holders of addresses. And this means it has two purposes. You can use it to repudiate routing for a prefix, or you can use it to require RPKI to be used to declare valid routes through RPKI. So the first one, you make an AS0 rower, you do nothing else. And if you don't make anything else, no one else can. They don't have your private key. So you declare things off limits in public routing if they're using ROV. The second thing, you do the same as the first thing, but then you make the specific rower for the prefixes you want to be visible with the origin AS that you want to assert. So here's a list of addresses for DCIX who hold resources under RIPE NCC. And you can see that there is a block of addresses in here that have a rower AS of 0. If you don't know DCIX, they're a large IX operator and they have a lot of addresses and they're meant to be used in the IX only. They're not intended for global routing. So let's consider a single prefix in this and look in a diagnostic tool. I like to use RPKI-Viz from ZDNS, which has been made by a colleague of mine, Dimar. And here you can see the validity of this AS0 origin and the certificate chain that goes from it all the way up to the trust anchor we operate. But this time, let's look at a rower made by Deutsche Telekom in Germany with a non-AS0 rower. This is a real operational rower for their Origin AS3320. And it says they can send all kinds of prefixes, and it permits them to route a /12 that they have from Origin AS3320. So this is how they say, we want to have this done. But let's have a look at another rower they've made. This is an AS0 rower. You may remember that we were looking at a /12. This AS0 rower repudiates the covering /11. It means they want only the /12 they showed before to be legal and publicly visible. The other half of this /11 is not meant to be visible in public routing at this time. So with the AS0 rower they've made, it prevents somebody else originating that half of the space. Now, let's talk about AS0 operated by a PNIC in RPKI. What exactly are we doing? So the first thing to note is a reminder, we're running two systems. The AS0 system is completely different to our main RPKI, and this is deliberate. It was to make sure that we isolated the system and contain its behavior and effect on BGP. We even run an independent code base, new code, different code, and parts of our mainline RPKI system have been repurposed. We use Krill for this system, which has been developed by NL Labs, and we're operating in VMs and Kubernetes. The reason we operate this system standalone should be clear from this slide. It's to make the system one which has to be deliberately used. We didn't want this system to apply automatically. And there are two guiding principles for the operation of this service. Firstly, we only ever sign objects which talk about the resources that are not delegated. Special resources, specific resources, and they show in our public delegated statistics reports as either available or reserved. And that's all we use AS0 to mark in this system. Secondly, we don't make AS0 statements for any other RIR's ranges. We only make statements for ranges APNIC can show is in APNIC's system of registration and delegation. Again, things that are listed in the delegated stats files or in the IANA registry or in transfer logs. So how does this relate to resources overall? The thing is that AS0 only ever signs over resources that you see in delegated files as available or reserved. It's the number of resources which are not delegated and shouldn't have contents that are delegated. When you, members, delegates of resources, make an AS0 rower, they refer to prefixes you hold, and you can't refer to undelegated or reserved or available ranges. They're completely complementary sets. They're opposites of each other, and they never overlap. So an AS0 rower that you see in the main RPKI thread under the main trust anchor for APNIC is a statement made by a delegate. They want you to use it. They want it to be applied in ROV. They want it to calculate routing validity, and you should use them. You should trust them if they're cryptographically provable because of their position under the main trust anchor. You should allow them to directly configure BGP. How do you do that? Well, you operate a validator that we talked a little about before, the code that checks validity. And this key concept of applying these ideas from validated outcomes to BGP depends on the concept of a VRP, the validated rower payload. These are the set of things that your validator, your relying party code, Routinator, RPKI client, Fort, whatever you run, has proved are valid in RPKI validation rules. And you can safely apply this to BGP using a protocol called RPKI RTR. And this will tell you if things seen in BGP are valid, aligned with a rower, or invalid, a rower would say you can't do this, or unknown. There's no rower that applies. The key point is we do not at this time recommend that you use the APNIC AS0 trust anchor and APNIC AS0 rowers as part of this BGP calculation. Use it for diagnostics. We're operating a service to keep the rower published exclusively for undelegated ranges, and the policy is quite explicit. The sole purpose is to repudiate BGP routes for undelegated resources. As soon as we delegate the prefix, it has to be removed from AS0, and our operational pledge is to complete this within 5 minutes of delegation. There's a variable propagation delay for this to become visible in global RPKI, but that's how quickly we apply it. That is actually the only operational boundary on our service. Now, APNIC as the Secretariat does not operate BGP to announce any space other than ranges which have been delegated to the Secretariat for its own use. So we are operating AS4608 and AS4777, and we have ASN for Anycast and research work, but the only prefixes that are announced by these ASN are the ones that we have been explicitly delegated as an entity or that we have authority to test. For instance, the bogon checks that we did on final/8. We've been instructed by the community under Proposition 132 that was accepted in our process to add the AS0 rower exclusively for undelegated and unassigned resources. Nothing else has been defined as valid for us to sign over in this service. And since we don't assert any other origin AS for these prefix, this is the only kind of AS0 rower that will exist for them. There won't be a rower that says, here is the positive routing assertion with a real origin. There'll only be the negative positive assertion, AS0. No AS0 rower created by APNIC will exist in the main RPKI system. So our operating model is really very simple. We keep this rower aligned to the visible state of the delegated files, but we do this at two slightly different intensities. When things are delegated, we make a change as quickly as possible before it becomes public. So we remove the prefix from the AS0 rower as quickly as we can, and we do this so the delegated account holder has immediate access to it and can assert valid RPKI as quickly as possible. But when a resource is removed from use and has been marked into reserved or available, we have a slower termination process and reservation process behind the scenes to make sure that there's no justified use of the resource. So the visible state of being declared reserved or available may not happen immediately. It's at the end of a very long process. And more importantly, it's not automatic. A hostmaster has to deliberately mark these ranges into a reclaim state for them to be marked into a place where we can use them in AS0. So we only add ranges to AS0 rower at the end of a long road. It's the last thing we do after holding it in registry. So originally, when this proposal came up, there was a possibility that we would do this inside our main RPKI. And we did a risk analysis and noted changes we made to AS0 would become immediately applicable to BGP. After review by the APNIC EC and APNIC's lawyers, we decided this wasn't a wise position to take, because everything else we do in the main RPKI is a positive assertion of delegation. And nothing we do other than this has a direct impact in BGP. It's filtered through route filter construction or other processes. Some things like reverse DNS, they do have direct immediate change, but that has a lower operational impact than BGP. So we decided initially, and for the foreseeable future, to make the AS0 rower under a unique different TAL. By making it under a different TAL, we made it necessary for everyone to explicitly choose to include it. We've turned it from an opt-out model where you would have to deal with it as a fact of life to an opt-in model where you have to accept it into your life. Combined with that, we made the decision to recommend not including AS0 TAL in default ROV calculation and only to use it for diagnosis. So, just to repeat, unlike delegated ROAs made in the mainline, we're recommending only in diagnostics. Here's two ways you can do that, using BGP Alerter or running a stub BGP service. BGP Alerter is a complex system. You're going to have to read about it from its developers, but it has a way to tell it to read the output of a validator as a set of VRPs in JSON format. Well, we can use that. With the system configured to read the AS0 TAL and products, you can configure BGP Alerter to get alerts when an AS0 event detects a breach in BGP of visible routes. I've tested this, and I would like to write up my experience of using BGP Alerter this way. The problem is that there are actually very few bogon updates and withdrawals, so I haven't been able to actually see a trigger of an incorrect routing event yet, but there's an interesting blog out there when it happens. Here's another approach, and this comes directly from Tashi-san in one of his tutorials. Tashi noted that there's the Bogon's root server project feeding virtually the same information as a special BGP feed using a private ASN. Because it's a private ASN, it's a non-transit service, and you can elect to take a feed of BGP data that in effect marks things for you. If you did the same thing with AS0, you could use this to tag your routes, to add information, to decide how to proceed. So Tashi suggests that you use a service like this. Operate a BGP feed of your own that understands AS0 and can mark bogon routes. So approach here would be to run a validator only for AS0 and to make VRP state only for AS0 and run RPKI RTR only for AS0 and put it on a stub AS inside your network. Take a feed of your real BGP, but don't announce any routes. Just use this to see a result of what happens, and then run a normal RPKI system with the main RPKI TAL integrated in BGP, get VRPs for this mainline, protect your routing. You now have two systems, one that directly configures BGP with RPKI trust, and one that configures a stub AS to tell you what you see. So here are some of the things.
GGM. Sorry to interrupt, but we're running a little bit over time. Can we wrap this up fairly quickly, please?
Yes, I will go as quickly as I can.
Fantastic. Thank you.
So one of the big questions is, what if it all went wrong? I'm here to reassure you that we won't be causing states that could break BGP. Our main RPKI trust anchor is a 0/0 TAL, and APNIX AS0 is a 0/0 TAL as well. So in theory, it could repudiate anything, but our operational model, our code, is constrained not to do this. There is no plan or intention to modify that operational basis. We have no intention of converting the system to sign over validly delegated resources. What if it did accidentally repudiate your resources? Well, the risk analysis here is quite simple. If we accidentally repudiate resources you hold, you can use RPKI to turn these things back on. But additionally, we have a 24-hour knock that you could contact and get us to update this service immediately. Other RIRs, well, there's been some conversation, but no one else is running service at this stage. That may yet come later, but that hasn't been determined. So for RPKI growth, you can go and visit some stat sites that we provide. Labs, for instance, can show you uptake of ROV worldwide. You can use tools like RPKI Viz. So in summary, APNIC AS0 is only being operated for undelegated. It's a turn it off service only for the undelegated resources. We don't use it to control visible active routing. We don't include it in our main RPKI system. We recommend that you only use it for diagnostics. And if you believe at any stage there's been a problem, please let us know. Thank you for letting me talk today. Sorry for running over, Dave.
That's perfectly all right, sir. Always good to have you here. Thank you, George. Any questions that you have for GGM, feel free to flick them to us and we'll pass them on. Or you might be able to catch up with him later on in the conference chat. Our next presenter is Bart Gantong, and he will be talking about the Khan Bank transformation to Sdn. Are you there, Bart?
Yeah, I'm here. Hi, Dave.
Excellent. Thank you. Get ready for your screen share when you are.
Sure. Thank you.
Yep, that looks good.
Okay, thank you. So, hello everyone, and my name is Harold, and now I work as a network administrator in a Khan Bank of Mongolia around 4 years. So today I would like to share my gained experience of the transformation project from the traditional network to the software-defined network that our team is working in last 1 year. And my presentation includes the brief solution of the software-defined network and some challenge that we faced and the results that we get from the 1 year project. And also, I will introduce some automation examples that we are using now. And at last, I have some future plans to implement in the SD-WAN solution for the branch connections. So first of all, I would like to share the concepts of the software-defined infrastructure. And as my point of view, there are the 4 general parts included in here. And those are computer resources, which includes the virtual machines or the containers. And also it will include the underlying parts, which can be the hypervisor, 6i, or the KVM hosts. And the next one is the SDN parts. And there are the virtual switching, virtual routing, also the firewall security functions, and it can be included the load balancers. And the third one is the storage solution. So the basically storage solution can be the active or the active standby. Basically, it should meet the requirement on the SD software-defined infrastructure, whether do we have the multi-site or the single site, how will the disaster recovery will be happening. And the last one is the automation parts. So it covers the software-defined network manager, and which is mostly manage all the virtual network devices by the API. And there is a container orchestration solutions. If you have the container environment Docker like this, and at last, there's a provisioning and orchestration tools like Ansible or the Terraform. So using those parts, we are able to build the software-defined infrastructure. So basically here, I have included a slide that how our computing resource environment is changing in my work, in my daily tasks, and how it is more virtualized and more flexible types. So at the beginning, we used the physical servers for 1 or 2 applications with the single operating system. Then we started to use the virtualization solutions. So as you know, it gives us the chance to operate the multiple operating systems on the single physical hardware. And plus, it can give us the redundancy and the flexibility, more functions and more benefits. And recently in my work, so the many systems and the many the functions business systems are shifting to the container solutions, and it gives us even more flexibility and more distributed environment to us. So this is for the comparing to the network side. So the next slide is about the network transformation that I'm also facing in our daily works, me and my team. So, and as I see, there are the three major changes in my daily work. So at the first, the few years ago, we mainly used the separate physical devices for the each roles or the each levels. As you said, we use this dedicated core switch, dedicated distribution switch, and access switches, which are all the dedicated boxes inside the one data center. So then we migrated to the virtualization solutions for the routing and for the switching. As you know, the VR for the routing or the virtual context for the switching level. And now we are moved most of our network parts into the software-defined solutions. So it includes the routers, switches, security functions, and also the load balancers. And all those parts are managed by the Sdn Manager and additional orchestration tools. Okay, so I just, depending on my research on the as a part of the project, so I just put some of the SDN solutions from the different vendors. So here's four of them are, for example, Cisco ACI and the VMware NS60, and there is the EOS and also the Juniper Contrail. So now let me talk about the transformation that we had last year. So at the beginning, we said, so it's more likely the goals, not the challenges. So at the beginning, we set the three main goals to be achieved by the project. So the first one is we have requirement to make the endpoint to move with the IP addresses across the different sites. So this is mainly depending on requirement from the application clustering behavior or the faster disaster recovery process. So keeping with this first point, we also need to keep the existing physical infrastructure. So which means we need to keep layer 3 connections, or we need to keep the security physical devices as it is where it is located due to the smooth migration process from the traditional to the software-defined network. And the last one is we want to automate the daily tasks. So this is the three main goals that we were targeting. So here's how our network gears are placing along with the computer resources. So there is a data center 1 and the data center 2, and of course there is a physical host, which can be the KVM or the 6R hypervisor, and of course there is a multiple applications, containers or VMs are standing on the each host. Then using the SDN, we're able to put the firewall functions inside each host, which can be bind to the every VM's virtual adapters, and it gives us the improved security with the zero trust solutions. So then we were able to run the distributed SDN virtual switches on the each host also. And at the last, there is a distributed routers with the distributed gateway, which can isolate the endpoints within the same hosts. And the distributed router gives the efficiency and the short path for the traffic within the same hosts between two isolated points. So two isolated points basically means even we have two VMs that is standing in the different subnet or the different zones within this single host. It can be managed through the distributed router within the host. And so the next, for the container parts, so depending on the vendor solution, we need to install the container network interface plugins, depending on the vendor solutions. So it basically manages the distributed routers and the switches, which is operating behind the containers. And then we also deployed the management cluster with the multiple physical hosts. So there we have the logical routers, which provide the dynamic or static routing between the Sdn network to the external network. And it basically keeps the role for the NAT, network address translation, and all the DHCP, and there's the other symmetric services. And then we have a logical firewall, which provide the network security functions, same as the traditional firewall, if we require to isolate the zones or the interfaces across the different subnets. And the next one is the Sdn Manager. So it gives us a control and the visibility of the whole environment. And at the last, we also have a load balancer, which can be either inline or the 1-hour mode, depending on our logical segment. And all of those parts deployed as a virtual machine, or either it can be the bare metal servers dedicated for only one rows. And using those network gears, we have deployed another level of the overlay network in our existing physical infrastructure. So which means we built the overlay network infrastructure on the same physical existing network infrastructure. Okay, this is the basic overlay design that we have. So here is I have listed the what we have changed and transformed it from our old infrastructure. So the first, we have moved all the traditional VLANs networks into the logical segment. So the logical segment basically means the encapsulated network that use the index inside the encapsulated network header. And also we replaced the physical switches and the routers by the distributed router. And at the third, we replaced the physical load balancers by the logical load balancers, which is standing inside the VMs. At the last, we migrated all of the firewall rules into the distributed firewall functions, which is more flexible and which also give us improved security with the zero trust solutions. Now let's move to the logical view of our overlay network. So there is a data center 1, and there's a data center 2, and both of the data centers have the physical core routers, and it is connected through the fiber, the dark fiber. And then there is a logical router, which is the tier 0 router. And this logical router is using the multiple VMs as active. In order to improve the redundancy of the edge router, we deployed each VMs inside the different racks, inside the different server chassis. And those edge VMs are connected to the physical router by the traditional VLAN network. Then we have deployed the distributed tier 1 router in each computer resource. So the difference of the tier 1 and the tier 0 is tier 1 can be only the distributed router, which can be distributed into each hosts, and it can have also give the distributed gateway functions to the each hosts. And we connect it logically to the tier 0 router with this tier 0 router. So as a result, we have created the one logical segment and connected it to the tier 1 router. And as a result, we are able to deploy or move the VMs across the multiple sites with the existing IP address and inside the same subnet. Also, we have one more T0 router for the site DR proposed, which locates in the DC2 as a backup. And it also connected to the core physical router, same as previous. And in DR scenario, we have automated the API scripts will help to connect it to the same logical segment in case of the failure or the switchover conditions. So the automated API will help to connect it to the same logical segment. And physical core routers and the tier 0s are configured as an OSPF neighbor, or it can be maybe another dynamic routing protocols, for example, BGP. And this is the infrastructure for the data center 1. And vice versa, we have another set of network environment, which is working as a primary in the DC2. So we have the tier 0 here, and then there's a tier 1 DR also. And there is also one more extended logical segment, which extended across the data centers. So here I have tried to show you the detail of the single site overlay network. And there is a tier 0 router connected to the physical infra. And then, as I mentioned, VMs are located in the 2 data centers with the single subnet. And there is a tier 1 router, and it is connected to the logical segment. And here is the VMs in the 2 data centers with the IP address from this one subnet. And so here, each VMs can have the distributed firewall or the IPS functions for the microsegmentation. And there is a bridge edge cluster. So the bridge VM is basically the handles the encapsulation and decapsulation process across the 2 different environments. Basically, if you have the physical server, which need to connect to the overlay network of the Sdn, then we use the bridge edge cluster and handles the encapsulation and decapsulation to pass through it. So as the site redundancy proposed, we deployed one more bridge edge cluster, another data center. Then we have deployed the load balancers in the 2 locations. One is for the traffic within the overlay, which means the east-west traffic from the one VM to the another VM inside the software-defined environment. And another one can be the north-south traffic and can be connected to the tier 0 edge router, and which are suitable to handle the north-south traffic, which means traffic from the external to the Sdn or from Sdn to the external. This solution gives us the fast and more simple disaster recovery steps. So for example, in case of the moving physical VMs from one site to another, we can relocate without any config change. Second is VM relocation can be fully automated across the data centers. Plus, the firewall or the security functions will move together with the VMs. No need to change the access list or the inspection policies. Okay, here we have the couple of the automation example in the network related daily tasks that we are trying to automate our works and try to have the more efficiency in our daily works. So the first one is network access list entry and the deletion task automation. So based on the security requirements, so the port opening, the port closing work takes a lot of time in our network security administrators. So that's why we take it as a priority one. And as you see the workflow here, when the end user open the ticket on the ITSM system, then the automation tool, which can be the Ansible, get the ticket from the ITSM tool. Ticket information, including the source, destination, IP address, or ports. And then the Ansible will check the current configuration from the Sdn Manager by the API, whether it is existing rule or it needs to be deployed. Then the next step is Ansible will push the ACL rules to the software-defined network manager, also by the API. Then after that, once the Sdn Manager get all the ACL information, then it will distribute these ACLs to all the SIG-side or the KVM hosts to distribute the configuration of the distributed firewalls into each VMs, depending on the necessity. At the last, when Ansible gets the confirmation from the Sdn Manager, it will close the ticket automatically on the ServiceNow system. So it is automation example one. And,
excuse me, Cyril, sorry to interrupt. In the interest of time, can you pick up the pace a little bit? We've got one more speaker to get through and I want to give him a fair allotment of time. Thanks.
Yeah, sure. Okay. So, okay, I will wrap it up quickly. So the automation example number 2 is just basically the same thing. And it is only for the differences. We use the automation for the load balancer configuration, and it is together with the provisioning of the VM. And the normal process is the same as before. And after the transformation work, we get the faster DR operation across the data centers, and we get the zero trust security solutions, and there is a traffic efficiency, and plus we are able to support the cloud native solutions. And when you see the graphs here, there is the huge efficiencies happened in the security and the network layer. So this is the graph and the result of our work. And so here I put some the learned lessons from the transformation, which is basically test well and get well knowledge about before you deploy. Basically, the thing is this. And for I have put the SD-WAN solution. The plan in next year plans to implement the SD-WAN solution, and it can be to include the edge clusters and using the multiple links as active, and we can use the x86 hardware for the routers and the VPN boxes, and the automated SD-WAN orchestrations for the provisioning of the new VPN boxes. And the expected result is we will get the zero touch provisioning and then dynamic path selection with the active links. So this is what I want to introduce to you, and thanks you all for your time. Thank you, Dave.
Thank you, Cyril. If you have any questions, please feel free to flick them to us and we will pass them on to Cyril for him to answer for you. Now, our third and final speaker for today is Hans Gredler, he's the CTO for RT Brick, and he's here to present his paper on disaggregated routing gets real in Deutsche Telekom. You there, Hans?
Hello, good morning. Good afternoon, everybody.
Good morning for you, I gather. Very early.
Yes, it is.
Excellent. Ready for you whenever you are, sir.
Yes, just try to share my screen.
Yeah.
You cannot start screen while the other participant is sharing.
Okay. Sarul, I think, must still be doing screen share. There we go. You should be right now.
Perfect.
Now, Hans, just to put you on a little bit of time pressure, you've got about 14 minutes tops.
Okay, I'll try to make that work.
Excellent. Thank you, sir.
By the way, can you see my presentation screen now?
Yep, all good.
Okay, super. So before I start, let me just put a note to George Michelson, the previous speaker, right? In previous life, I was a routing protocol engineer at a large router vendor, and I was implementing RPKI router protocol. That was actually 11 years ago, and it's always a moving moment to see the technology you have been working on finally is getting deployed and proves out to be useful. So thank you for that. Today, I'm not going to talk about RPKI router. I am talking about a deployment of disaggregated routing in a telco environment. Just a little bit of landscape here. I'm the CTO of RT Brick. I'm obviously a software vendor, but we have been working on that architecture throughout the last 3 years in close collaboration with the engineering and architecture team at Deutsche Telekom. So what you find here is, of course, not any product feature. It is more 3 years of learning and tinkering and turning an idea into something which can get deployed. We started about, as I've mentioned, 3 years ago. There was already a BNG deployment at Deutsche Telekom and across 1,000 locations across Germany and also multiple other countries. I will come to a minute why this turned out to be not optimal. Meanwhile, after 3 years, we have deployed a disaggregated internet access service, classical triple play service, using a 1 gigabit internet service, including voice and video. We did this using open hardware, white box hardware, which is also closely aligned with the telecom infrastructure project, the Open BNG initiative. And as a result from that learning, the operator crew has also published the Open BNG white paper with some of the findings and asks for that. So why was the existing BNG network not good enough? Well, one problematic area is the area of modular chassis. The idea is you deploy a modular chassis, you populate it with core line cards, you populate it with access line cards, and you usually anticipate a lifespan of that equipment of 4 or 5 years. Now, what typically happens is that, well, there is updates, right? There is more modern line cards. There is sometimes upgrade to a line card triggers, upgrade to fabric cards. what you typically have to do is swapping cards, if not swapping entire systems. To present day, Deutsche Telekom has 4 teams roving throughout the country, just doing 250 days per year, just doing replacements. And that ongoing replacement throughout the equipment life cycle has, of course, a bit of overboarding operational expense to it. So when we wanted to actually build a 4th generation of an access system within DT, we wanted to make sure that we don't really do it with chassis-based routing systems, but rather use 1, 2 rack units, fixed size configurations, and make it work using standard protocols. And in a nutshell, this is essentially what we really did here. We have replaced all the proprietary internal control plane within the chassis, all the proprietary encapsulation to exchange packets between the line cards with something standard-based. Standard-based as in we have heavily bet on BGP, labeled unicast, VPN unicast for the control plane protocol. And we already have a very nice fabric routing protocol. It's called IP-MPLS. And that use of those 2 protocols really ensures that you can extend the fabric over time. If you need more capacity on the core side, hey, fair enough, just add a bunch of spine routers. If you have new services, if you develop new services and do not really want to do a forklift upgrade, no problem, just deploy additional leaf switches here at the bottom and without really rip and replacing the rest of the pod. What particular hardware we have been using? We have done several experiments starting from x86 throughout Intel, Barefoot, Tofino, throughout Broadcom Silicon, and we have ended up with the Broadcom Jericho Silicon product line, mostly because it had all the packet processing function that we need, and it actually had a very nice traffic managing module, especially for BNG applications where you need to do queuing, shaping, handling the triple play service all in distinct queues. We could very easily model that on that chipset. We've started here with 800 gig chipset at the beginning. This is shipping. This is deployed right now in the network. But soon this is going to get superseded by the next generation of Broadcom Silicon. This is a chip called Qumran 2C, by and large a 2.4 terabit system, along with a very large TCAM that we use for classifying and mostly doing counting work. The hard thing for this kind of deployment is, and this has been a bit of the learnings of the early SDN adventures that we did, is you cannot really bet on a green field, right? As much as I like architectural visions all around OpenFlow, the problem is there is already a vast amount of networking technology being deployed, and you really have to fit into that brownfield. So one of the design constraints that we have been given very early is we cannot really change any of the external interfaces. So that means talking to the core, we cannot really avoid having a full implementation of BGP, ISAS, including segment routing. And on the access side, we need to implement PPPoE, L2TP for provider wholesale partners. And for the management plane, we needed to implement radios along with, I would say, 40 extensions to certain proprietary radios attributes. What is a core principle here is that idea of the fabric. So that means we have added here horizontal scalability, right? That means we can scale out if we need additional households, additional subscriber ports. We can just add here leaf switches. And if we need additional backbone capacity, we just add core switches. Now, the previous speaker has been talking about SDN, and we tried to figure out what is the thing that traditional protocols are doing good, and at what point do we need control for it. By and large, also adhering here to the brownfield constraints, we have been using routing protocols. However, we have added a certain service selection layer on top of that. What does that mean? It means on the left-hand side, talking to the core routers to the backbone, within the fabric, we use traditional IP MPLS routing protocols. We have also, I'll come to that in a minute, also add certain auto discovery elements. So the provisioning really becomes a one-touch operation. Where we add programmability is at the leaf, where we have implemented certain access lists, qualifiers, match conditions, where we can identify flows. And we have exposed also via an API what particular actions to follow on, like, hey, pick a certain VRF doing an IP route lookup. Select here a certain queue shaping profile. If you do not really want to process the traffic here locally, push pop a certain tunnel header on top of it. The core of the fabric is BGP, but really BGP, like it is being deployed in many data centers of the world. Most operators know BGP, that you have to explicitly configure your peers. We did not do that. What we are doing here is adding an auto discovery capability to BGP, particularly by using IP version 6. So we are using the link local router advertisements of the neighbor discovery protocol to discover new peers in the fabric. And then we auto establish a BGP session using the link local addresses. That, of course, gets secured using MD5 and TCP/AO authentication to really ensure that we are talking to the right party. So why are we, what we're bringing up next is essentially a labeled unicast service. Why labeled unicast? Everything that runs on top of this fabric is actually an overlay service. So even if at the leaf we are deploying a BNG service facing the subscriber, the connectivity across the fabric is essentially like a L3 VPN, where the services VRF actually gets connected here to the corresponding backbone port. Why did we do that? Simple answer, we wanted to have multi-tenancy at play. As you can imagine here, this is a regulated environment, and of course you need to provide access to other service providers in your region, and that level of isolation helped us to keep things separate. Another thing that turned out to be an interesting engineering challenge is how to attach those fabrics to the backbone. We have using here and deploying Anycast scheme. Why is the Anycast scheme? Well, basically the BGP next hop as emitted from the spine routers is getting sent to the backbone. And as I've mentioned before, the spine routers are horizontally scalable, i.e. there is usually 2, 3, 4, even more at large sites. Now, you do not really want to have that BGP next hop floating around because in the core, each additional BGP next hop is causing some forwarding state burn, right? And since we have many of those little boxes, there was actually concern that we're burning too much forwarding resources of the transport routers in the core. By just using one BGP next hop as per each pod, we ensure that the transport requirements turn out to be moderate. How does the operating system look like inside the bare metal switches? What was most important is the external view. So everything that we actually keep running here on that system needs to get exposed using open source telemetry tools. So DT Operations is a heavy user of Grafana. We sample pretty much all of the 400 interesting scalars in such a system using the Prometheus time series database. And we use Kubernetes for deploying our app. What is our app? Our app is essentially a container that runs a stock Ubuntu 18.04 distribution along with some additional packages. Additional packages could be, the onboard Prometheus for sampling data or anything else that you want here, plus roughly 15 different packages which implement the routing protocols that run on such a node, as well as the forwarding abstraction. Let me also say that the forwarding abstraction in telco environment turned out to be a bit of a tricky thing, because with all those fabrics, with MPLS, with various tunneling technology and potentially recursive tunnels, you have to really have a wild zoo of mix and match technologies, and we therefore have decided to make that forwarding puzzle solver, just like anything else here, a pure user space application that can get restarted and upgraded anytime. What we did learn along that journey, stable APIs is a heavy mandate here. We started here with very diverse teams, operating system integration groups, the GPON integration team, the BNG, the backbone integration team, the SDN controller grew, and in the formative year, we had a lot of flurry of APIs that got changed almost without notice. So we figured out that very early on, you need to finalize your API definition and rather redo a certain API than change existing one. We figured out also that the base layer that we have on the switches, on the white box switches, which is Open Network Linux, turned out to be good software integration point. Pretty much every white box vendor that we have been working with, so that is Delta, that is UFI-Space and EdgeCore, had their own private ONL fork with good support for their hardware and periphery. And decoupling whatever you do here from the ONL base layer turned out to be a really prudent decision. Consequence for telcos is there is a lot of new tooling. So that whole CI/CD style of development, handling Kubernetes-based analysis tool, new telemetry tools like Prometheus and Grafana that required really a lot of training, a lot of investment in people. And well, that just takes time, but you are really empowering your operations to early detect any issues and support the network in a faster, better way. One other thing is actually a non-technical one. We figured out that you need to change here a bit the support and also the procurement process because disaggregation means you are sourcing one piece of hardware from one party and one piece of software from the other party. And most most operators in that space have boilerplate contracts here, which all assume that they're purchasing and procuring integrated system. So one of our learnings, and in fact this took a 6 to 9 month journey, was really separating that, making sure that procurement has got the respective document templates for sourcing hardware and software independently. Also, furthermore, once you have multiple parties in there, also in the troubleshooting and triaging process, you need to expand a bit the SLA process. Here in that way, we have hardware, we have the routing, the signaling application, and also you have maybe something that goes wrong on the base OS layer. So you need to all factor in all those individual troubleshooting times and expand here the usual window. In our case, this was from 4 hours from 4 hours to 8 hours. Well, and that gets me to a much speed up delivery and the end of my talk. Any questions you have?
Excellent. Thanks for that, Hans. As we are running very over, if you do have any questions, please feel free to flick them through to conference@apnic.net and we will pass them on and get them answered. I'd like to thank Hans, Sarul and GGM for their papers today, and we will have to quickly run away now because we have another session to get to. If you could please indicate on a poll that should have just popped up how you felt that this session went, that'd be really good. So for me and all the speakers, thanks a lot, and we'll see you at the next session.